So now we're going to talk about bases that are not base 10 for logarithms. And as I mentioned before, we can essentially put anything we want there. So our logarithmic scale for our diameter of sphere situation, we used exponents of power as 10. So using 10 as the base for logarithms is common since the number 10 is the base of our number system, right? There are other bases, like binary has a base of it's just zeros and ones. There's many other number systems that we don't often encounter in daily life. However, there are other numbers we could use as the base for logs. For example, you could use exponents of powers of 5. So in other words, base 5, or exponents of power of 2, base 2. So let's look at some base 5 logarithms. It looks like this. We would say log base 5 of 5 to the 4th is equal to 4. Do I like how they said this? Log base 5 of 5 to the 4th power equals 4. And then log base 5 of 25. Ooh, wait a minute. 125. That 125 is not a base of 5. Well, right, it is. If we rearrange it, we should recognize that 125 is really 5 to the 3rd power, so that answer is 3. And then log base 5 of 125. 1 over 25? Oh, hey, do you remember how we learned in a previous section that when we are dividing, we can rewrite this with a negative exponent? So this could be 25 to the negative 1. And then I know what 25 is in terms of a base of 5. That's the same thing as 5 squared. So I could really write this as log base 5 of 5 squared to the negative 1. And we all know from our properties of logarithms that we can rewrite this as a single logarithm. Just multiply those two exponents together. So we'd have log base 5 of 5 to the negative 3rd, and now we know the answer to this logarithmic expression. Log base 5 of 5 to the negative 3 is negative 3. Wow, isn't that great? Here are some examples of base 2, same idea. So if the number is not a base 2, you want to look to see if it can be written as a base 2. And since 16 is really 2 to the 4th, we're good to go. Okay, so here is a general statement that is super useful. A statement in logarithmic form looks like this. Log of some base of x equals y. You don't need the parentheses. I sometimes put it in there. B represents the base of the logarithm. X is the power of b, and y is the exponent. So the base of b for logarithm can be any positive number except 1. Okay, so we could write the restrictions on this b as being b could be greater than 0 and not equal to 1. So it can be a number between 0 and 1. It can be a number greater than 1, but it can't be 1 itself. Now, if I was to rewrite, I guess that's coming in the next section. Hang on, I'm going to relax here for a minute, because in the next section, we're going to look at how can we rewrite this in exponential form. So this is, you should think of this as log form of an expression. Okay, so we're going to determine each of the following things here. What's log base 4 of 64? Well, if I can rewrite 64 with a base of 4, then I'm good to go. Now, it turns out I happen to have this one memorized. You may not, and that's okay. Just start dividing 64 by 4 as many times as you can. You may remember this from a previous course. Let's see, 64. 4 goes into 6 2 times, remainder of, 2 times. Who said that? 4 goes into 6 once, remainder of 2. So bring down that. We got 24. 4 goes into 24, 6 times? Ooh, and there I know that 16 is 4 divided by 4. So this tree tells me these are factors of 64, and I can rewrite 64 as 4 cubed. Well, then I'm just going to take log base 4 of 4 to the 3rd power, and since these bases match, all I have to, the answer is 3, because the log of base 4 is the exponent of a number to the 4th power, an exponent of a base 4. You can see the language gets a little wonky here. All right, let's check out how our our authors got log base 2 of 1/16 to be -4. This is a tricky one. So I think the first thing we want to note is we probably want this thing to be not division. We don't tend to like division in here. So I'm going to rewrite it as 16 to the -1 power. That property of exponents, if we undo the division, we'd write it as a negative exponent to bring it to the top. If it's in the top and we want to make the exponent positive, we turn it into division. Next, I'm going to note, wow, can we rewrite 16 in terms of 2 to a particular power? You might know this offhand. Awesome. I'll show you this tree thing. You could also use a calculator to do this. I'm just repeatedly dividing 16 by 2. Really what I'm saying is 2 times 8 is 16, 2 times 4 is 8, 2 times 2 is 4. And then note that this is really log base 2 of 2 to the 4th power raised to the -1 power. Well, and then from our previous sections, we know that for the -1 power, you multiply these two together, and we get log base 2 of 2 to the -4th power. That means the answer to this logarithm of 2, log base 2 of 2 raised to the -4 power is -4, because this exponent is what the logarithm is equal to. All right, question C there in the textbook is asking what's log base 3 of 9. I'm hoping you're looking at that and saying, I know the answer. I've got it. Log base 3 of 9, that is, well, let me show the steps though. What you should be thinking is, oh, I know that 9 is 3 squared, and so the base of this exponential piece and the base of this logarithm are matching, so the result is its exponent. All right, last one, letter D. We're looking at log base 3 of 1 over 27. Again, hopefully you're like, hey, I know that 27, division by 27 is the same thing as 27 to the -1 power. And then 27 is just 9 times 3. And I already knew that 3 times 3 was 9. So 27 is really 3 cubed. Can't forget that we were dividing by that 27, so it would be to the -1 power. You're going to multiply. I'm going to skip this step now, and we're just going to say that's -3. Okay, so our textbook now rewrites this and gives us this property of exponents. And it says, in general, log base b of b to the n is equal to n, provided b is greater than 1 and b is not equal to 1. So I've kind of been like foreshadowing this when I say as long as the bases match between the expression part that we're evaluating the log of and the base of the logarithm, then the answer, the result of that is just n. So here comes 4 examples on question 8. I'm going to keep writing them on this blank sheet of paper. I think it's a little easier for me to keep track of them. So 8a says, what's log of 1? Now, this is tricky. Maybe it's not too tricky, but first off, you might have forgotten, since you are just now encountering logarithms, that the actual base here is 10. In all of the problems in MyMathLab, in the textbook, all the things we throw at you, we're not going to give you the 10. You're going to have to remember that it's there. Okay, so let me rewrite it without the 10. This is how it was handed to us. And so the question we need to ask ourselves is, can I write 1 as 10 to a particular power? And again, this is a little tricky. You might be thinking, no, there's no way. It is. Remember that anything to the 0 power is 1. So I can raise 10 to the 0 power. 10 to the 0 power equals 1. So this is the same thing as this. And since our bases match, 10 and 10, the result here is 0. Okay, get ready. Check out B. Log base 5 of 1. Okay, again, can I write 5 in terms of can I write 1 in terms of an exponent with base 5? You might be getting suspicious of what I'm about to do here. I can write this as 5 to the 0. So what is this result? Well, since this is 5 raised to the 0 power and we're evaluating log 5 of that, 0. Boy, what? Now they're saying log of 1/2, log 1/2 of 1. What is that? Can I write 1/2 to as using a base with a power that results in 1? So what would I have to raise 1/2 to get 1? Turns out I can't, it's 0. So here's the point. In general, there's a couple more options up there to look at, but we don't need to. Oh, I guess we do need to. So then D. Well, let's generalize these things. What we should note is if we have log base B of 1. Now we have to keep the conditions of B, right? It has to be greater than 0 and not equal to 1. Anytime we see this, where our B value is a valid option in our logarithm, the result is 0 every single time. Okay, let's do the next one, then I'll pause for another video. And then for D, notice we have, we're asking what's log of 10? Remember, these bases match, so this is a power of 1, this is really a power of 10, so the result here is 1. E says, what's log base 5 of 5? Partly why we give these examples is often students, when you're introduced to exponents, you forget that every single number you learned all the way back to first grade had a power of 1. We just never told it to you. It wasn't necessary at the moment. But that's easy to forget. So then when you're evaluating log base 5 of 5, you're like, I don't know what that exponent is. Well, now you do. It's 1. And then F here, log 1/2 of 1/2. So what is the exponent on this? It's 1. That's what the logarithm is looking for. And then in general, our statement here is that log base B of B is always 1. But this is just, so to mathematician, we're like, yeah, duh, we knew this. When we wrote log base B of B to the n equals n, all we've said is that the n here is 1. And mathematicians have seen that pattern. We recognize that pattern. And we wouldn't need to write this. But I think it's helpful for you all as you're growing into your mathematical prowess to keep track of these special cases, is what we call these.